getting back to our pizza recipe. Our simple recipe was 1 crust and 5 ounces of sauce and 2 cups of cheese will make 1 pizza. And we talked about how we can use that to predict how many pizzas we could make from a given amount of stuff. Well, what if we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce? How many pizzas can we make? I'm hearing 4. 3. 3 is the correct answer. So how do you figure that out? How do you even go about starting to figure that out? Well, you say, well, 4 crusts, I could make 4 pizzas. That one's easy, right? 10 cups of cheese. Well, I need 2 for each pizza, so I could make 5 pizzas from that, right? And 15 ounces of sauce. This one involves a little more thinking. 5 ounces for each. 15 divided by 5 is 3, so that'll only make 3 pizzas. I'm going to run out of sauce, right, when I get to 3 pizzas. This is the same thought process that we're going to go through for limiting reactant problems. So what we were doing in our heads is we were calculating the amount of product from each amount of reactant. So 4 crusts, and just like the mole to mole ratio, we can use our recipe, you know what I mean there. 1 pizza, 1 crust. 4 pizzas. 10 cups of cheese times 1 pizza out of every 2 cups of cheese, 5 pizzas. 15 ounces of sauce, 1 pizza for every 5 ounces. So 3 pizzas. It's fairly easy for us to think about this because we've all at least seen someone make a pizza, right? We can imagine this process, and so it's more concrete and less abstract. So the answer then of how many pizzas we can make, we're choosing the smallest one because we recognize that when we get to 3 pizzas, we've run out of the sauce. Are there crusts left? Yeah, there's a crust left. Is there cheese left? Yeah, there's cheese left. Can I make a pizza out of that? No, maybe I could make cheesy bread, but that's not pizza, right? So the smallest one of these is the amount of product we can make. Well, can't I just add 4 and 5 and 3 and say, well, I could make 12 pizzas? That doesn't make any sense, does it? It's just the smallest one because it stops there. Any questions? So here it is in pictures. The 4 crusts will give us 4 pizzas. 10 cups will give us 5 pizzas. 15 ounces will give us 3 pizzas. So this is called the limiting reactant or limiting ingredient because it limits how much we can make. This is the least amount of product. That's how much we could make. Okay? So we say that the tomato sauce is the limiting reactant, limiting ingredient, limiting reagent. And the number of pizzas we could make using up all of that limiting reactant is the theoretical yield. If everything went well with our pizza making, back here, if everything works out, we could make 3 pizzas. There's no way we can make 4. We don't have enough stuff. Could we end up with fewer than 3 pizzas? That's possible. You know, you got distracted watching cute cat videos on TikTok, and you didn't hear the timer go off and you burned one. Now you've only got two. Or your dog jumped up and started eating it, right? Stuff happens. So the ingredient that makes the least amount of pizza is your limiting reactant, and that determines how many pizzas you can make, the theoretical yield. In reactions with multiple reactants, just like when we're cooking, it is very likely that we will use up one of the reactants and not the others. Right? It would be very unusual if you set out to make a batch of cookies and you had just the right amount of butter and chocolate chips and sugar and flour and eggs in your house and nothing extra. Right? That would be really weird. It would be hard to go to the store and buy just the right amounts, right? There's almost always going to be some left over. So those reactants that are left over are said to be in excess. There's extra. So one thing gets used up, that's when the reaction stops, and everything else just sits there. The amount that is actually made is called the actual yield. You might burn one, drop one on the floor, dog might be an issue, etc. So what if we only make 2 pizzas and we could have made 3? Well, how do we say how efficient we were at making pizzas? We can talk about a percent yield. So that's going to be how much we actually made, divided how much we should have been able to make. And then the percentage is times 100. So if you made all 3 pizzas, your percent yield is 100, you're doing great. But if you screwed up on 2 of them and you only made 1, well, then you've got 1 out of 3 or 33% yield. And if the people at the pizza place that you're applying for a job for know about this, they might not want to hire you because you're not very efficient, right? So this is kind of a nice slide because it has all of those terms on one slide and gives their definitions. I'm not going to read it all through to you. A nice way to have a good copy of a slide like this that you might want to have is to go on Canvas, and I've got a link there to the PowerPoint slides. You open that, and then you get that slide that you want on the screen of your device and take a screenshot. Right? And there you have it. Beautiful. It's in your photos. You can find it easily. Let's apply these concepts to a chemical reaction. We looked at the combustion of methane. 1 methane molecule would react with 2 oxygen molecules, making 1 CO2 molecule and 2 water molecule. Well, what if we have 5 molecules of methane and 8 molecules of oxygen? Which one's going to run out? Well, we're going to do the same thing we did with the pizza. We're going to take that one ingredient and how much we have. So we have 5 molecules of the methane, and then we're going to look, the product we're interested in here is the CO2. We can make 1 CO2 for each one of these, just like the crusts, and so we could end up with 5 CO2 molecules. And then we're going to do that with the other ingredient, the oxygen. There's 8 oxygen molecules, but the equation tells us we need 2 oxygens for every CO2. So this would only make 4 CO2 molecules, 4 pizzas instead of 5 pizzas. So which of those ingredients, those reactants, is going to get used up? The oxygen. Because we're making CO2 molecules, think of it like making pizzas, we're making pizzas, and then we run out of O2, we have to stop. We have to stop making CO2 molecules. So this is the one that runs out first. It's the one that gives us the smallest amount of product. So that's the limiting reactant. The amount of product given by the limiting reactant is the theoretical yield. If everything works like it should, we can make 4 molecules of CO2. Stuff can happen in chemical reactions as well. Any questions? Yes?
Why don't you use this one?
Why don't I use the H2O? That's a great question.
Or do you always use the first?
So we could use either one. Yeah, we could use either one. We're doing the CO2 because we started out talking about greenhouse gases and finding out how much CO2 was put into the atmosphere. So the CO2 is the one we happen to be interested in. You could also do it in terms of water. And the one that makes the least amount of water would be the same. It'll still be the oxygen. Yeah, great question. Anybody else? Okay, so here we have nitrogen and hydrogen forming ammonia. Got a balanced chemical equation. 1 nitrogen and 3 hydrogens making 2 ammonias. So we have this flask here on the left. It contains a mixture of the reactants. We have identified the blue ones are the nitrogen and the white ones are the hydrogens. Which of the following images best represents the mixture in the flask after the reactants have reacted as completely as possible? So let's just draw some groups here, right? For every 1 nitrogen, we need 3 hydrogens. So here I've got a nitrogen, and I'm going to put him with 3 of the hydrogens. And what's that going to make? It's going to make 2 molecules, right? This one group is going to make 2 molecules of NH3. Well, I've got another nitrogen over here. So that nitrogen and 3 more of the hydrogens, I can make 2 NH3s out of that. What's going to happen to those hydrogens that are sitting there? They're in excess. They're just going to sit there. Just like the extra cheese on your kitchen counter when you finish making the 3 pizzas, it's just still there. So then we look at these guys over here, and we're looking for 2 plus 2, 4 of those compounds, right? The compounds look like this one. So here, this one has 2 of them. This one has 4 of them and nothing else. This one has 4 of them and the 2 hydrogen molecules. So which is the correct answer? C. It makes 4 ammonia molecules, but we can't ignore that excess reactant, right? We have 2 hydrogen molecules here that didn't react. Here, this is stoppered. Nothing's getting out. We can't have things just disappearing. They were there, and so they're still here. They are still hydrogen molecules because there wasn't any more nitrogen for them to react with. Does that make sense? So when we get quantities of reactants given as masses, which is more typical than molecules, we need to calculate how much product we can make from each reactant. And then we're going to use the smaller amount. So this is how your book shows it, and this is entirely valid. It's a fine way to do things. What I prefer to do is to just go ahead and calculate the grams of product from each of them. I'm just going to do 2 grams to moles to moles to grams. Do that for the one reactant. Do grams to moles to moles to grams for the other reactant. And then the massive product is the smallest one, just like with the pizzas. We couldn't make the sum of all those different pizzas because that was silly. We couldn't make the largest one because there wasn't enough of the other ingredients. It's always the smallest number. So take each of your reactants, pretend like it's the only one, and then calculate the amount of products, and then pick the smaller. If you want to do it the way the book shows, that's absolutely fine. Okay, here's an example. We have a reaction mixture. Let's start that one over. A reaction mixture contains 42.5 grams of magnesium and 33.8 grams of oxygen. What's the limiting reactant and theoretical yield? Suppose that the actual yield is 55.9 grams. What's the percent yield? So many questions. Well, let's just identify what we're given. We've got some numbers here. And here's another number. And then we're going to go in and highlight the questions. So they want to know what the limiting reactant is, the theoretical yield, and the percent yield. We don't have to answer all of those at one time. Anytime we have stoichiometry, a chemical reaction with quantities, I like to use the chemical equation to organize this information. It gives me a better visual of it. So this much magnesium, I'm going to write the mass of magnesium under it in the equation there. So that tells me 42.5 grams of that, 33.8 grams of oxygen. Actually, I'm going to take advantage of colors. 33.8 grams. And then the question is, how many grams of this? That's one of the questions. Another question is, which one of these gets used up? Well, identifying the limiting reactant and calculating the theoretical yield, those come from the same process. So we'll calculate the yield from both reactants. We'll pick the smaller one, that's the theoretical yield, and then the reactant that gave it to us is our limiting reactant. We'll worry about the percent yield after we do that. So I'm going to do grams to moles to grams of my product. Here there's only one product, so we don't have to decide which one we're looking at. So 42.5 grams of magnesium. Grams of that to moles of that. Grams to moles, moles of the thing we're trying to find, to grams of the thing we're trying to find. This is like probably the most important kind of calculation in Chem 1A. Mass to mass stoichiometry, grams to moles to grams. So we need to get good at this particular calculation. Once you're comfortable with it, it's not hard. Yes, it involves writing some things down and doing some calculating, but the process is not hard. And we're just going to do the same process 2 times. We're just repeating this pattern with some different numbers. So grams to moles to grams, and I'm going to take this unit and pull it down here. And this is why we call it dimensional. Oh, what did I do? I put it in the wrong place. It's over here. I was zoomed in too far. We're analyzing the dimensions, the units. So we're figuring out what the units are going to do. And then we use that to tell us where the numbers go. Here we have our moles in the middle. This is always a simple whole number ratio, and it just comes from the coefficients in the balanced chemical equation. This tells me that 2 moles of magnesium are going to make 2 moles of magnesium oxide. So I'm going to get 2 moles of magnesium oxide for every 2 moles of magnesium. Could I simplify that? Yes, but it's not worth the effort. Just leave it. The first and the last one are going to be molar masses. The magnesium is easier because magnesium is an element, so we just look at the periodic table, 24.31. 24.31 grams is 1 mole of magnesium. And we do have to calculate the molar mass for this guy. It's the mass of magnesium plus the mass of 1 oxygen. Yep, making mistakes all over the place. That's a 3, not a 5. 24.31 plus 16. So 40.31 grams of magnesium oxide for 1 mole. Any questions? I believe quite strongly that you should do it just like this. Put all the things together, do the calculation in one swoop instead of writing down intermediate values. It's faster and you'll have fewer errors. Okay, so I've got 42.5. I just multiply by the top, divide by the bottom, skipping the ones if I feel like it. Times 2 divided by 2, those cancel out. You can multiply and divide by them or not, it'll be the same. And so this is going to give me 70.4. I'm always, thinking about sig figs in the back of my head, and usually it's the number we start with. So here it's 3. So this one's going to have 3, and then I'm just going to write down 2 extras to avoid rounding errors. So that's the amount of product that we could make if we use this amount of magnesium and there's enough oxygen. Now we're going to do a very similar calculation with the other reactant. Grams to moles to moles to grams again. But this time we've got 33.8 grams of O2. So we're going to go to moles of O2. And then we're going to go to moles of magnesium oxide, our product. And then we're going to go to grams of product, magnesium oxide. This unit comes down here, so they cancel out. This unit comes down here. And this unit comes down here. Again, I like the middle part first. So I'm going to look at my balanced chemical equation, and there is an implied 1 in front of the oxygen. So it's 1 mole of oxygen is going to make 2 moles of magnesium oxide. Just like getting the numbers from the pizza recipe. Here I have my oxygen measured in grams. I need to see how many moles of it we have. Well, this is O2, so it's 2 times the mass of oxygen. So 1 mole of that is 32.00 grams. This last piece is exactly the same as in the first one. That's kind of why I like to just do two complete calculations instead of stopping at moles and comparing which is bigger. It's very little extra work, but it's less thinking, and then you're just done. So the molar mass of magnesium oxide is still 40.31. So 33.8 times 1 divided by 32 times 2 times 40.31. And again, sig figs, there should be 3. And now we may have forgotten why we were doing this. What was I trying to do again? I got so wrapped up. Okay, so here's our question. How many grams of magnesium oxide? So this is like the pizzas. We took the sauce and the crusts and the cheese, and we figured out how many pizzas we could make, and which of those answers did we choose? The smallest one. Because we understand that when we get to the smallest one of the ingredients has run out. This is the smallest answer. When I make 70.472 grams of magnesium oxide, I've used up all the magnesium. I can't make any more. This is where it stops. So this is the smaller one. And that equals the theoretical yield. So we could say the theoretical yield is equal to, and this would be where we would round, 70.5 grams of magnesium oxide. This number is not going to be the answer for anything. Okay? Okay, so I just identified the theoretical yield. What's the limiting reactant? The magnesium. I find the smaller one. I look back at what that came from. That's my limiting reactant. There's some worksheet problems where you have to do some work much like this. And it's important to identify what your answers are. An advantage of having that quiz is that it's going to force you to pick one answer. Sometimes people will do these two calculations and not box or write anything else. And yes, it's beautiful work, but you still haven't told me what the theoretical yield is, right? So there's my theoretical yield. Here's my limiting reactant. Suppose the actual yield is 55.9. This is how much actually got made, because some things didn't work out quite right. Sure, a dog didn't get in here and you didn't burn it, but something happened, right? Percent yield is the actual yield divided by the theoretical yield times 100. It's the part that actually got made divided by the whole amount that could have been made times 100. In this problem, it actually says the actual yield is this. Sometimes they don't say it so clearly. They might say 55.9 grams were made. And we need to recognize that they are telling us the actual yield. All homework problems, they're going to have to tell you what the actual yield is, because there's no way for you to know. When we do an experiment in lab, we actually collect something and weigh it, right? We did that on Tuesday. We collected an amount of copper at the end. That was the actual amount that we got. And there we called it percent recovery, but we took what we ended up with at the end and we divided it by what we should have gotten, which was exactly what we started with, right? And so if everything went perfectly, you'd have 100% yield. but it's almost always going to be less. So here's my actual yield. I'm going to plug that into the equation. So we actually made 55.9 grams. We could have made 70 point. Now I'm going to use the unrounded value here because that's just better. And I'm going to multiply that by 100. 55.9 divided by 70.472 times 100. And here again, I didn't mean to do that. This has 3 sig figs, and I underlined this. This also has 3 sig figs, and so this answer, also with the 3 sig figs. But I'm going to write down 2 more. When you're writing down the 2 extras, if this second one needs to be rounded up, go ahead and do that. But if you don't do it, it's not going to affect your answer. And then we're going to round this. I apologize for the unexpected pause. We'll just pick up where we are. This question doesn't say anything about limiting reactants in the problem. The title says limiting reactant, but on an exam there's no titles to the questions, right? How do we recognize that we have a limiting reactant problem? It's when they give us information about more than just one of the reactants. If they only told us we had 5.22 kilograms of hydrogen and they didn't say anything about the nitrogen, what we would assume is that there's plenty of nitrogen. Or they might say this much hydrogen and excess nitrogen. And that says, oh, you don't need to worry about that, there's plenty of it. But here they're giving us amounts of 2. So we have masses of 2 reactants. We need to do 2 calculations. We get 2 answers, and we pick the smaller one. Okay, so our general path is grams to moles to grams. Do we have the mass in grams? No, we don't. We have the mass in kilograms. There's more than one way that we can deal with this. This question, we want to end up with kilograms. We're starting with kilograms. So one approach is to leave the kilo there and just say, but I'm not going to cancel it out. I'm just going to let it go through. I'm not going to cancel it out. And then it'll still be there at the end. Another approach is to add a step. Kilograms to grams, and over here, grams to kilograms. These steps are going to end up canceling each other out. So I've got 2 calculations here. I'm going to do one way on each. So on the first one, we're going to go ahead and convert to kilograms. From kilograms to grams. So grams to moles to moles to grams. So I have 5.22 kilograms of hydrogen. What does kilo stand for? Times 10 to the 3. So this is a real fast way to convert this. What if instead of writing kilo, I write what it means? So instead of writing kilo there, I'm going to write times 10 to the 3. That's the same thing. This is like we did at the beginning of worksheet 1. Writing it without the prefix, using its meaning. That works great at the beginning, doesn't help us much at the end, but okay, so now I've got my grams. I'm going to go to moles of hydrogen. And I'm trying to find out about the ammonia at the end. So I'm going to go to moles of NH3. And then I'm going to go to grams of NH3. And then what do I have to add on at the end there? Kilograms. So I complete these units in the denominators, making sure that I'm actually crossing out matching things and not just imagining things. And then I need some numbers, right? Well, let's do the moles in the middle first. This is from the chemical equation. 3 moles of hydrogen make 2 moles of NH3. So in my mole ratio here, I'm going to have 3 moles of hydrogen and 2 moles of NH3. Because that's what my chemical equation tells me. Moles and grams, those conversions are molar masses, right? H2, 2 hydrogens, so that's going to be 2.016 grams. So 1 mole of hydrogen is 2.016 grams. Over here, I need the molar mass for ammonia, 1 nitrogen, and 3 hydrogens. So that's 17.034 grams. Is 1 mole. Out here at the end, I need to convert from grams to kilograms. The kilo is in the top here. Kilo stands for 10 to the 3. 1 kilogram is 1 times 10 to the 3 grams. The prefix and the 10 to the something are always on opposite sides of each other. So now I can do this calculation. And I'm going to use the EE or EXP button on my calculator. I'm not going to use e to the x or 10 to the x or times 10 caret something. You can make those other things work, but they will also get you in trouble. And your scientific notation button is much faster. So if you haven't gotten familiar with it yet, let's do that today. Okay, so 5.22. And when I press it, I'm saying EE because that's what's written on my button. What I see in the display is just an E. That's fine. I'm not going to press it twice. As I press EE, I think times 10 to the. And then I'm going to press 3 for the exponent. Multiply by 1, divide by 2.016, multiply by 2, divide by 3, multiply by 17.034, and then I'm going to divide by 1 EE 3. I don't need parentheses there because my calculator understands that that is a single number. It's not 2 numbers that I'm multiplying. If you don't do it correctly, instead of dividing by 1,000, you end up multiplying by 1,000, and now you're off by a factor of 1,000,000. Not so good. Okay, so this is what my calculator is giving me. We're expecting 3 sig figs, so 29.4. My calculator says 039, and it bothers me not to round that up, so I'm writing 04. Any questions? Okay, let's do the other calculation. 31.5 kilograms of nitrogen. I wrote the prefix kilo in red because I'm not going to cancel it out. I'm just going to leave it there. This is the representation of a number, 10 to the 3. I want to have a kilo at the end, and so if I don't cancel the kilo out, it's still going to be there. So I'm going to ignore the kilo. So I'm going to go from grams of nitrogen to moles of nitrogen to moles of ammonia to grams of ammonia. I'm not canceling the K, and so when I get here to the end, it's still here. I'm just going to let it hang around. So I'm going to divide by grams of N2. That cancels grams of N2, but does not cancel the kilo. It's like another variable, like an X or a Y or something. It's just going to sit there. It's just going to be K. Here I've got moles of N2, cancels moles of N2, moles of NH3, cancels moles of NH3. I like to do the mole ratio in the middle first. Here I've got 1 mole of N2 for every 2 moles of NH3. So there's 1 mole of N2 for every 2 moles of NH3. My first conversion factor relates grams and moles of nitrogen, so I need the molar mass of N2. So 1 mole is 28.02 grams. I've memorized a lot of these molar masses because I use them so much. It just makes things faster. I don't expect you to have them memorized. You just find out on a periodic table. This one, grams of ammonia to moles of ammonia, is exactly the same as the conversion factor we used up here. So all we have to do is copy it down and use it. So if I look at my units here, there's a K that didn't cancel out. Everything else got canceled out except grams of NH3. So my unit, grams of NH3, is there, and the kilo that I never dealt with. 31.5 divided by 28.02 times 2 times 17.034 equals 38.299 kilograms. So I showed you 2 slightly faster ways of dealing with the kilogram-gram thing. This would be the full path where you'd have 1, 2, 3, 4, 5 fractions. And there's nothing wrong with doing that. This is not a race to see how fast you can get the answer. It's how reliably can you get the answer. And so maybe there's a shortcut to Costco, but you get lost when you take it, right? Take the long way that always gets you there, right? That's what we should do with these problems too. So what's my answer? This is the smaller one, right? So I can make 29.4 kilograms of ammonia. Any questions? I have figured out a way that I can share essentially the screenshot with you. So if you haven't gotten it all copied down, or you're afraid you didn't get it copied down quite correctly, I will be posting that on Canvas later today. So you can look at that. 29.4 kilograms. So here's another one. It's asking for the limiting reactant, theoretical yield, and percent yield. Do you want to see another example, or are you feeling okay with it? Another one? Okay. More examples are better. Mining companies use this reaction to obtain iron from iron ore. The reaction of 167 grams Fe2O3 with 85.8 grams CO produces 72.3 grams Fe. Determine the limiting reactant, theoretical yield, and percent yield. So these are the numbers I'm given. And I'm finding limiting reactant, theoretical yield, and percent yield. I don't know about you, but I'm hot. Too warm. Okay, so I am going to take those numbers and write them under the equation. 167 grams of Fe2O3, 85.8 grams of carbon monoxide, and 72.3 grams of iron. Are they giving us the theoretical yield? Is this the theoretical yield? It says this much is produced. That's the actual yield. They have to tell us that because there's no other way we could know. We have the information to calculate the theoretical yield, but this guy, this is our actual yield. So when it's worded like this, it can be a little confusing.
When it gives you the actual yield, we're going to use that one for
The percent yield.
Yes, okay.
Yeah. So the reason they're giving us this actual yield is because they're also asking us for the percent yield. But what we calculate here, and here we're looking at iron. So we want to know how many grams of iron could be made from these ingredients if everything goes right. There's another product here, CO2. We don't care about the CO2. We're not going to do anything with it. So I have amounts of two reactants. I'm going to do two calculations. Grams to moles to moles to grams. So 167 grams of Fe2O3. Grams of that to moles of that. To moles of the thing I'm looking for, to grams of the thing I'm looking for. And then I'm going to fill in the units in the denominator. Someone from one of my other classes was texting me yesterday before the exam and saying, I don't understand why this is this. And that was just the perfect question that you should be texting me. Like maybe you're trying to do a problem like this at home and you're like, I don't understand why we don't use this number yet. Or I don't understand where this mole ratio comes from. Or why did you go to moles of Fe and not moles of CO2? There's all kinds of things that you might have a question in your mind about. And those sorts of questions are kind of hard to look up and find. But if you ask me, I can answer it really quickly. And so I answered his question, and he's like, oh, that makes sense. I understand it now, right? So cleared up the whole thing for him with one little text exchange. So you are not bothering me when you're texting me. Remember that? It does bother me when people start apologizing for bothering me, so don't do that. Okay, grams to moles to moles grams. Where were we? Moles in the middle. Fe2O3 has a 1 in front of it, implied. So I'll put a 1 down there. The Fe, come here, pointer, has a 2. Here, I need the molar mass of Fe2O3, so I'm going to have to calculate that. And yes, you could just type that into your calculator and not write it down. I highly encourage you to write it down, because then if you get the wrong answer, you can go back and look at how you calculated that, run it through the calculator again, and see if it was just a dumb button error. 2 times 55.85 plus 3 times 16, 159.7. 1 mole, 159.7 grams. The other end, we're dealing with an element, so we just pick its mass off the periodic table. Just double check that I'm remembering that correctly. So we've got all of our numbers. We just plug them into our calculator. And write down the answer. As is often the case, we should have 3 sig figs. That said 805,886. I didn't round up. It doesn't matter on that one. Okay, halfway there. Take the other reactant, 85.8 grams of carbon monoxide. Grams to moles to moles to grams. Grams of carbon monoxide to moles of carbon monoxide. To moles of iron. To grams of iron. There's moles in the middle, 2 Fe, oops, that was an eraser, and there's a 3 in front of the carbon monoxide. I need the molar mass of carbon monoxide. .01, and then my molar mass for that last term hasn't changed. .114.05 grams of iron. So I'm looking for the limiting reactant, the theoretical yield, and the percent yield. One of these is my theoretical yield. Which one is it? The smaller one. So it's this guy. So when I record that as my answer, I'm going to round that to 114 grams of iron. What is the limiting reactant? Yep, CO. This is my answer. I'm going to go back and see what gave me the answer. That's my limiting reactant. And then I'm going to calculate my percent yield. So the percent yield equals actual yield over theoretical yield times 100. They gave me the actual yield. I calculated the theoretical yield. I'm going to use the unrounded value. 72.3 divided by 114.05 times 100. 63.391%. So up here, my answer is 63.4%. Any questions? Well, that's kind of colorful, isn't it? Yay, got the right answers.